Good morning. It's a pleasure to be here to tell you about the work of a large group of people who you'll see getting credit as the slides go on for communication avoiding algorithms. I will talk about linear algebra. I have to talk about machine learning, of course, but we go way beyond that to any code that looks like nested loops. So before I tell you how to avoid communication, I want to tell you why we want to avoid communication. Algorithms have two costs, measured in time or energy, doing the arithmetic or the logic, and moving the data, which we are going to call communication. And in this talk, communication is going to mean either between different layers of a memory hierarchy, between cache and DRAM or multiple layers of cache, or between different processors over a network. So the model I'm going to use to ask, is my algorithm optimal or not? Have I hit a lower bound in how much I communicate? I'm going to count three things: how many flops the algorithm does, how many words it moves over any one of those wires, and how many messages it sends. What's a message? You take a bunch of words, put them together in one big lump, and send them all at once. And that's because there are three different hardware costs for those three things: the time per flop, the time to move one word, or the reciprocal of the bandwidth, and the time for one message to get from one end of the wire to the other. That's the latency. And the last two terms are the communication. So these three are properties of your algorithm. These three are properties of the hardware. And it's sort of well known that those three hardware parameters are orders of magnitude apart, and they're growing apart exponentially. Even with the end of Moore's law, they're still growing. This is some old data. So they're all improving. So the time per flop was getting better at 60% a year. Everything else was improving, but more slowly. So what this means is these are far apart. They're getting farther apart. So even if your algorithm is not dominated by communication today, it may be next year or the year after that. So we certainly want to avoid communication to save time, and it's exactly the same story for saving energy. If I change the units from seconds to joules, it'd be the same story. So the goals I have are to redesign algorithms to avoid communication. That means between all levels of a memory hierarchy and going between processors, all of that. And for many, many algorithms, what we've done is we've proven new lower bounds that we didn't know about before. And once we got those lower bounds on communication, we looked at the standard algorithms and libraries like LAPACK and ScalaPACK and many others, and it turned out they were all doing asymptotically more communication than necessary. And so we've been redesigning all the algorithms from many different fields and getting very large speed-ups and energy savings. So let me give you some samples. So the first approach that we did was we take an algorithm and we're going to do the same operations just in a different order. So for matrix multiply, for example, which is a very highly studied algorithm, it turned out people were not doing it right, and there was a 12x speedup that they'd left on the table by communicating too much. And I'll tell you that story in more detail later. If you want it, that's for dense matrix multiply. For sparse dense matrix multiply, there is even more of a speedup, 100x. Where does that algorithm come up? It comes in things like fMRI and machine learning algorithms like that. You don't have to do linear algebra per se. I'll sort of tell you what this, what the assumption is here. You can do, logic, maxes and sums, and in that case you get graph algorithms like all pairs shortest paths, and you can also do, Nbody codes, which are even simpler, and you get an 11.8x speed up there. So the next thing you could do is use a different algorithm but get a mathematically identical answer, modulo round-off, of course. So I'll tell you in some more detail about an algorithm called TSQR, or tall skinny QR, which has gotten very large speedups, for example, 13x on a GPU. Symmetric eigenvalue problem. BiCG-STAB is an iterative algorithm that is used in a bottom solver in various applications in DOE. And then, beginning with machine learning, coordinate descent, 5x speedup. And then, if we go on and look at machine learning more generally, it's sort of the Wild West. What's the right answer anyway? So let's try a different algorithm, come up with a different approximate answer, and we can get even larger speedups there. Most recently, 135x for ImageNet training, getting it down to about 11 minutes. So this work's gotten a lot of recognition. So a few years ago, I was teaching this dense matrix multiply algorithm in my graduate course at Berkeley, and a student thought it was a good idea, and he created a startup, and a few years ago, it was acquired by Intel for their machine learning activities. So the tall skinny QR algorithm, this 13x thing, won a best paper prize at supercomputing, and we got it finally into LAPACK about the same time. And the support vector machine, that won a best paper prize. in 2015, and this 135x speed up won another Best Paper Prize. So I will go into a little bit of detail about these, but obviously I can't go into all the details. So here is the outline. I'll start with linear algebra. I'm going to kind of organize this by applications. I'll tell you what the communication lower bounds are for classical, which means smells like three nested loops, direct linear algebra. And then I'll review the previous classical matrix multiply routine and ask, do they attain the lower bound or not? Then I will do better than what people thought was best before. That's what I'm going to call communication avoiding 2.5 dimensional matrix multiply. I'll explain that definition. Then tall skinny QR, and then I'll do iterative methods and talk about GMRES and by CG stab. Then we'll move on to machine learning and talk about lasso and training neural nets. And then I'll tell you how this all generalizes to arbitrary code that looks like nested loops accessing arrays where you can have arbitrary subscripts. So that pretty much covers a lot of code. So let me summarize the communication bounds for classical order n cubed linear algebra. So it's basically one theorem that covers anything that smells like three nested loops, so not just matrix multiply, but solving AX equal B, least squares, eigenvalue problems, and the SVD. As I said, these are mostly not attained by the algorithms in the standard libraries, and so we've been busy inventing new algorithms to do it. And as I said, it's not just doing the same operations in a different order, i.e. loop transformations. We have some new numerical properties, new output formats, new ways to encode the answers, and new data structures, and so I'll tell you about that. Now, the theory has a pretty simple model of how the hardware works. Hardware is complicated, and so ultimately you need to do some more tuning, and auto-tuning is one of the best ways to do that. You search for block sizes that are around the ones that the theory predicts, but the theory sort of gives you a pretty narrow space of things to try. And all of this applies to sparse matrices, not just dense matrices. It's the same theorem, but of course whether you can attain the lower bound depends on the sparsity structure. If you want to multiply two diagonal matrices, there's no magic there, right? You just do the obvious thing, but there's a lot of sparse matrices that are dense enough where you can get big speedups. And let me just say it's the similar story for iterative linear algebra. So here's the lower bound in one line. So let M, I'm going to use capital M throughout the talk, as the size of the fast memory. So your data is too big to fit in memory of size capital M. How much data has to move in and out of that small memory? So in the sequential case, you can think of that as the cache size. In the parallel case, you can think of that as the local memory on one processor, and the memory on other processors being the slow memory. So the theorem says that the number of words moved per processor, if it's parallel, in and out of this fast memory is lower bounded by however many flops you assign to that processor to do, divided by the square root of its memory size. And that's sort of the universal theorem. Now, in the parallel case, you have to use this, you need to assume some load balance, right? Because if you had a parallel machine and you only used one processor, you wouldn't do any communication, and this wouldn't be relevant. But if it's load balanced, then this is exactly what you get. Now, this has been known for a very long time for matrix multiply. People have been proving theorems about this going back to 1981, Hong and Kung in the sequential case. But now we know it applies to just about everything. All the basic linear algebra subroutines, LU decomposition, QR, eigenvalue, SVD, tensors. Of course, tensors are more than three nested loops, but it's the same idea. They smell like three nested loops in a mathematically precise way. It applies to some whole programs, so sequences of these operations, no matter how you interleave it. So if you want to compute a power of a matrix, it's a bunch of matrix multiplies. No matter how you interleave all those operations, it's the same lower bound. It applies to both dense and sparse matrices. In the sparse case, the number of flops is no longer n cubed. It's whatever your sparse matrix wants, but it's the same lower bound. It applies to sequential and parallel, as I said, and it applies to some graph theoretic algorithms like all pairs shortest paths with Floyd-Warshall, because you don't have to do multiplies and adds, you just have to access data and do something with it. So that's the lower bound on the bandwidth, the number of words moved. I also want a lower bound on the latency, the number of messages. So the simplest way to get a lower bound on that is to always send the largest possible message. And then that's going to minimize the number of messages I send. So it's the number of words moved divided by the largest message size. What's the largest message? It's the whole memory. So the lower bound on the latency is just going to be this lower bound divided by m, because the largest message is of size m. And so that's what our goal is for all algorithms, to get to this lower bound. And this won another Best Paper Prize. OK, So let's review the previous matrix multiply algorithm, both sequential and parallel, and ask what they do. So this is going to make sure we understand what data movement is. So here's the most naive possible matrix multiply 3 nested loops. And the innermost loop is just taking the dot product of the ith row of A and the jth column of B. There it is. So now let me annotate this very simple code with some comments that say where the data moves. And so what I'm going to do when I get here is I'm going to read this row of the matrix A into fast memory. So I'm assuming my fast memory will hold a whole row or column, but not the whole thing. Then the next loop, I read in that entry, and I read in that jth column. And now my inner loop can take the dot product. I have the whole row and the whole column there. And when I'm done, I write C back to slow memory. So this is the naive nested loops. Let's count the total amount of data movement. I read each row of A exactly once. So I read the whole matrix n squared times. I can't do better than that. Read A once. I read C once. I write C once. The expensive part is B, because for every row of A, I have to read every column of B. So I have to read the matrix B n times, and so there's an n cubed there. So altogether, I'm doing order n cubed reads and writes, and that completely dominates the 2n cubed arithmetic, because reading and writing is so much more expensive. So what's the classical approach to fix this? I'm going to do blocked or tiled matrix multiply. So it's going to look like 3 nested loops, but now I'm looping over little b by b blocks. So each one of these little blue squares is a b by b block. So it's going to be 3 nested loops. I'll read in this little b by b block of C. Then I'll read in that block of A, block of B. And this line of code is another 3 nested loops doing a b by b matrix multiply to update the C. And then when I'm done, I'll write C back to slow memory. So let's do the counting again to see how much data I've moved here. So I'm going to assume I can fit 3 b by b blocks into fast memory at a time. So I'll read in that b by b block of C, of A, of B, and then the inner loop is all going to happen in cache. And so I can do the counting. How many times do I read and write all of these entries? N over b, the quantity cubed. Each one is of size b squared. So the total amount of reads and writes has gone down by a factor of b. So it went down from n cubed to n cubed over b, and that's much, much less than the amount of arithmetic, so it's faster. So clearly, I want to make b as big as possible. So there's going to be some limit to how big I can make it. So I'm assuming that I can fit 3 b by b blocks into fast memory, so that means that 3b squared is at most m. And so I can pick b to be roughly the square root of m, and therefore I get 2n cubed divided by the square root of m, and that is my lower bound. So this is the classical way of attaining the lower bound. So at this point you might ask, okay, that's a nice way to write the code if I know my hardware intimately, but what if I don't know m? Or what if I have not just one level of cache, but many levels of cache? Well, if you're a Ninja programmer for Intel, then you'll write not 6 nested loops, as my code just showed, but 9 nested loops or 12 nested loops, and you can go on and on for that. They do that. Or you can use something called a cache oblivious algorithm, which is just doing it recursively. Break your n by n matrix multiply up into n over 2 by n over 2 matrix multiplies, and you can prove in theory that does a great job too. Although in practice, people want the last constant, so they tune matrix multiply with great vigor. Okay, that's the sequential case. Let's go on to the parallel case and say what the state of the art was. This is called Summa, which is short for Scalable Universal Matrix Multiply Algorithm. And the way this works is, suppose I have p processors. I'm going to lay them out on a square root of p by square root of p grid. So in this case, each one of these little squares in this 4 by 4 grid represents both a processor and a submatrix. So that processor owns that particular n over 4 by n over 4 submatrix of A and B and C. So what does the algorithm do? It's going to take each block column of A. So this is B columns and n rows. It's going to broadcast it sideways. It's going to take this block of B rows of B, little b rows of matrix capital B, and broadcast it down. So this processor, for example, all these arrows means it does a broadcast of this n over 4 by B matrix sideways, so everybody here gets a copy. This gets broadcast down, so everybody gets a copy. And when each processor receives its sub columns and sub rows, it multiplies them and updates the local matrix. And so it just marches across, as red marches from left to right and the blue marches from top to bottom. And if you do all the counting, excuse me, there's the code. It's quite straightforward. This actually hits the lower bound. Oops. So let me just sort of summarize that without doing all the algebra. So I'm going to have n by n matrices on p processors. I'm going to assume that I have one copy of all the data. That seems like a reasonable assumption. So that means I have n squared data altogether, and each processor is going to get one piece of it. Then what are the lower bounds? The numerator is the amount of work you do. It's load balanced. Everybody does n cubed over p. And the denominator is the square root of the memory size, and that turns into n squared over square root of p. And Summa doesn't indeed attain that lower bound. And the number of messages is smaller by a factor of m, and it attains that too, a total of square root of p messages. So the first question we asked ourselves, OK, now we know this applies to all of linear algebra. What about all the other algorithms in scale-a-pack? How do they do? Well, for the number of words moved, they mostly attained these bounds, except for the non-symmetric eigenvalue problem. It did asymptotically more. But for the number of messages, they were almost all asymptotically worse. They did much, much more than this, except for Koleski. So again, we started inventing new algorithms to attain all these lower bounds up to factors of log p. And so we have new algorithms for all these different things. But once we did that, we asked ourselves, can we do better? Now, why am I asking that question? Aren't we already optimal? Well, I made an assumption, and the assumption was that I was using as little memory as necessary, right? That there was one copy of the data spread across the machine, but the lower bound is true if I use still more memory. So the question is, can I attain it? If I can afford to have 2 or 3 or 4 copies of my data, can I go faster? Well, there was a special case known for quite a while, and it used this rather funny amount of extra data. So and it's been reinvented many times. And it assumes that you can have exactly p to the 1/3 copies of all the data. So if you have 1,000 processors, it assumes you have enough memory for 10 times 10 copies of the data, which is not necessarily realistic. So the question is, can you always use all your data, all your memory optimally? And that's called 2.5D matmul. So what I'm going to assume is that you have enough memory to have exactly c copies of the data. C could be 1 or 2 or 3 or whatever. And so that means each processor is going to have c times the minimum, n squared over p. So what's the algorithm going to do? It's going to take my p processors and lay them out in layers. They're going to be c layers and p over c processors on each layer. So here's what my grid is going to look like. This is why it's called 2.5-dimensional grid. And so, for example, if I have 32 processors and I can afford 2 copies, I'll have 2 layers. So let me index the processors in that way. And initially, all my data is just going to be sitting on the top. So this processor here will own that submatrix of A and B. So it's the same setup as before. So what's the algorithm? Each processor takes its copies of A and B and broadcasts them down. So every layer gets a copy. Then at each layer, everybody does 1/2 or 1/7 of the Summa algorithm. The algorithm I just showed you, it just computes like 1/2 of the partial sums. And when I'm done, all the partial sums that I need are sitting on top of one another, and so I do a vertical reduction so that everybody in this column adds up their stuff, and the true value of C, that submatrix, appears in the top layer. And so this is the new matrix multiply algorithm. And the question is, what speedups can we get? Well, up to 12x is what we measured. And so here are some examples on a 64K IBM BGP, and it turned out that 16 copies was the right thing to do. We could have had more or less. 16 was a tuning parameter. So here's an example with an 8K by 8K matrix. And here's an example with a much larger 131K by 130K matrix. And so we have communication in red, idle time in blue, and computation in green. And you can see we got rid of 95% of the communication. But even the computation went faster. So how could that be? We're still doing the same number of flops. That's because the local matrix multiplies were larger. And so I got better cache performance in each node. So the local BLAs were faster. And that's how I got a 12x speed up. In the bigger case, you can see that computation is now about 1/3 of the work, and it's running at full speed. And so I still got rid of 95% of the work of the communication, but now it's totally dominated by the computation. But if this is where all your energy went, I still may have gotten rid of 95% of your energy costs. So that depends. So the same idea extends to LU, to QR, to many other algorithms. And I should say that in the case of matrix multiply, it achieves a property called perfect strong scaling. So what that means is that if I have a machine and I'm running matrix multiply and I double the number of processors, I double the amount of memory, I use this algorithm and it scales perfectly. The communication time goes down by a factor of 2 and the computation time goes down by a factor of 2. And we have an energy model, a rather detailed one, that shows the energy consumption also goes down by a factor of 2. So this won a Best Paper Prize as well. Okay, so that's LU and so forth, and matrix multiply. Let me move on to something where we need a different algorithm, which is tall, skinny QR. Are there any questions, though? Please.
Does that imply you do the specific topology?
I'll talk about that later. So it turns out that for all of dense linear algebra, a 3D topology is enough, a 3D torus. But we also have lower bounds on the topology, but I'll mention that briefly at the end. But 3D is enough for linear algebra. Okay, so let me talk about how to do the QR decomposition of a tall, skinny matrix. So suppose my matrix is spread out over 4 processors, and each processor owns 1/4 of the rows, as shown here. The first step of my algorithm is going to be not to communicate at all and just do a local QR decomposition. So everybody just does the QR of their local submatrix. Now what have I done? I've implicitly factored this tall, skinny matrix into the product of this block diagonal orthogonal matrix times a stack of 4 triangles. Right? That's what I've implicitly computed. Of course, I don't want 4 triangles here. I want 1 triangle. But that's the first step of the algorithm. Then I take those 4 triangles, and I break them up into pairs. And for each pair, I do a QR decomposition. So here I have to communicate, but communicate something rather small. And what I've done here is I've implicitly factored this stack of 4 triangles into that block diagonal orthogonal matrix times half as many triangles. One more step, I take the last 2 triangles, just do a QR decomposition of them, and I'm done. What I've done is I've factored my original matrix into the product of that orthogonal matrix times that orthogonal matrix times that orthogonal matrix times R. That's QR. It's just a different data structure, a different layout. And my output can look like that. I can actually reconstruct the usual format, but the natural output, it looks like this. Okay, so that's, in some detail, the parallel algorithm. Let me sort of summarize it a little bit more briefly. All I've done basically is called MPI reduce or map reduce, whatever lingo you like, where the reduction operation is a QR decomposition. So all I'm doing is passing up these R matrices up to the top and getting a QR. So that's the parallel algorithm. What about the sequential algorithm? It's exactly the same, except I use a different shape reduction tree. So suppose that my cache is so small I can only fit 1/4 of the rows of the matrix. So what I'll do is I'll read in the first 1/4 of the rows, do QR, read in the next 1/4 of the rows, stack R00 on top of W1, do QR, read in the next 1/4 of the rows, do 1 more QR, and so forth. So in this case, I've read the matrix from slow memory to fast memory once, and 1 is obviously a lower bound. You can imagine something more complicated. If I have a dual core machine, I can have some parallel QRs going on as well as reading stuff from slow memory to fast memory. But what if I have a real computer? You know, it's multi-core and multi-socket and multi-rack and out of sight and all of this. I'm just going to choose the reduction tree dynamically. So whatever hardware is available to me at runtime, I'm going to use that optimally to compute the QR decomposition. So what that means is that every time I run it, I may get a different output. But mathematically, it still represents what I want, but it's no longer the same QR decomposition every time. So here's some performance speedups that we've collected over time. 8x speedups on an 8-core Intel Cloverton. 6.7x on a Pentium 3 cluster. This is kind of old data. 4x speedup on 32 processors of a Blue Gene. 13x on a Fermi, on a GPU. I mentioned that one before. This next one here was interesting. Jack Dongera and his folks did this experiment on 4 computers connected over the internet in 4 French cities. And you can imagine the bottleneck was the latency going from one city to another, and there was a 4x speed up over 4 cities. So that was a perfect speed up there. And for cloud computing, you can implement this using MapReduce, and it's only 1.6 times slower than just accessing the data twice. So it's very close to just doing 2 MapReduces, which is the minimum you need to do. The best speed up we got was infinite, and that was when the student doing this work, Mark Homan, who some of you may know, he's trying to run this on his laptop on a matrix that was so big it didn't fit in memory, so it had to use the disk. And the classical algorithm just thrashed the disk, and he got tired of waiting for it, and so he just hit Control-C. But the new algorithm only ran twice as slow as though there were infinite DRAM, as though the disk weren't there. And so that's what we call infinite speed up. I should say that if you're doing an SVD of a tall, skinny matrix, it's almost the same speedups because you do a QR and then you do the SVD of the little R matrix. So you get those speedups there too. And this won a best paper prize. OK. So now let's go on to iterative methods. I've been talking about direct methods so far. And so think about a Krylov subspace solver or an iterative method for either solving a linear system or an eigenvalue problem. Where does the time go? I'm going to do k sparse matrix vector multiplies with a and some starting vector. I'm going to build up a bunch of vectors that's going to span what's called a space, a subspace, Krylov subspace. And then I'll look for the best solution, whatever that means, inside that space. And there's a whole slew of different algorithms that do this, conjugate gradients, GMRES, and so forth. So my goal is to minimize the cost here. And I'm going to assume that my matrix is well partitioned in a sense that I'll make clear with some examples. So in the serial case, what does a conventional algorithm do? Suppose my matrix is too big to fit in cache, and I take k steps of one of these algorithms. Every time I do a sparse matrix vector multiply, I have to read my big sparse matrix from slow to fast memory. So the cost of communication grows proportional to the number of steps. We can take one step, read the matrix once from slow memory to fast memory, and take k steps of the algorithm. And so 1 is obviously a lower bound. That's the sequential case. In the parallel case on P processors, what's the conventional algorithm do? Every time I do a sparse matrix vector multiply, I have to do a dot product or something like that to do the update. So that means I have to do a reduction. One reduction costs log P messages. I do it k times, and so I'm going to have k log P messages. We can take those same k steps with one reduction, or order 1 reduction. And that also gives us big speedups. So there's lots of speedup possible. I'll show you some examples. The price is we're going to do a little bit of redundant computation. If your matrix is well partitioned, it's not too much. So the challenges are poor partitioning, preconditioners, that's an ongoing research area. I won't talk about it today, and numerical stability that I'll say more about. But let me just give you an example now of how we transform GMRES from the standard implementation to the new one. So what does GMRES do? It takes I want to solve AX equal B. It computes a bunch of vectors that span this subspace, and it chooses the best vector in that span to minimize the residual. So that's the algorithm. And what's it do? I take k steps. I do a matrix vector multiply times the last vector I've computed. I do one step of modified Gram-Schmidt. That means I make this vector here, W, orthogonal to all the previous vectors. And then I do a little update of a little k by k H matrix. And when I'm done, I solve just a little k by k least squares problem with that matrix H that I built. OK, so what's the new algorithm do? I'm going to compute in one step that I'll explain a different basis for the same Krylov subspace. I'm going to compute all of these powers of a vector times a matrix. This is called the matrix powers kernel. And I'll get a new basis for the same space. Then I'll run tall skinny QR to get a Q matrix. Q is going to play the role of all these V's that I had over here. Then I can build my little k by k matrix H from the R factor. And then I solve the same little least squares problem with that H matrix. So in the sequential case, the number of words goes down, moved between DRAM and cache goes down by a factor of k. And in the parallel case, the number of messages also decreases by a factor of k. So for those of you here who know about floating point and numerical analysis, does anybody see the obvious terrible bug in this algorithm? Everything that I've told you is true in exact arithmetic. This is a floating point problem. So what happens when I do these matrix vector multiplies over and over again? These vectors are converging to the dominant eigenvector. They're all becoming nearly parallel, and W is terribly conditioned. And so I lose precision completely. And I can show you convergence plots. That's a laugh, because they don't converge. They just bounce around. And so, but the fix is actually not too hard. Instead of computing a squared, a cubed, I'm going to use different polynomials. And if I choose these polynomials correctly, I can make these vectors pretty numerically independent, and it all works without increasing the cost at all. And there's interesting mathematics behind how you compute these polynomials. And so here's some sample speedups. A 2.3x speedup for GMRES on a small 8-core Intel Cloverton, and a 4x speedup for BiCG stab. This is in a bottom solver of a big science application at LBL. So I've already explained how to get tall skinny QR to go faster. Let me now talk about how to compute this matrix powers kernel. And I'm going to illustrate it for a very, very simple case, a tridiagonal matrix, which is very simple, so I can show you every detail. And so I have a matrix X, which has 32 entries. And I want to compute A times X, A squared times X, and A cubed times X, where A is tridiagonal. And this is small enough that I can show you every detail. So in particular, here's the dependencies. If I want to compute that entry of AX, it depends on exactly 3 entries of X, because it's a tridiagonal matrix. And to keep my PowerPoint a little simpler, I'm just going to color in that triangle. So everything at the top of the triangle depends on everything at the base. And this, of course, repeats itself. That entry of A cubed X depends on those 3 entries of A squared X. And if I just continue the dependency graph, it all the way eventually depend on all those entries of X. Now, of course, I don't want to compute just one entry of A cubed X. I want to compute a bunch of them. So there is the dependencies for, for computing all those entries of A cubed. So now I know enough to tell you what the optimal sequential algorithm is. So suppose I can only afford to fit about a quarter of my data into cache at one time. So I'll read in the first quarter of the rows of A, the first quarter of the entries of X, and then I can compute everything inside that blue trapezoid because I have all the data necessary without touching, and only touch the data once. Then I'll read in the next quarter of the entries of X and A, and I can compute everything inside that red parallelogram. So I have to keep a few extra entries from before, but that's small potatoes, stuff on the border. Then I can compute everything in the green region and everything in the yellow region. So I've now succeeded in computing all of these entries by only reading the matrix A once. That's the sequential algorithm. So what about the parallel algorithm? What I'd like to do is compute so now I'm going to assign each processor to compute 1/4 of all the entries here. And so processor 2 should compute everything inside that rectangle there. But eventually, it's going to also need to compute everything on the outside here in these 2 triangles. So the way I'm going to minimize, and so what it would normally do is I'd have 3 steps of communication. I'd compute that entry, and that entry. I want to just send 1 message, not 3 messages. So it's quite simple. Processor 1 will package up all those 3 entries down there and send it in 1 message to processor 2. Processor 3 will package up those 3 entries and send it to processor 2. And then processor 2 has all the data it needs to compute everything in that red trapezoid. And so every processor does the same thing, and everything in these overlapping regions gets done more than once, but that's a lower order term. So that reduces the communication step to 1. So that is for a tridiagonal matrix. Of course, interesting matrices are more complicated. So let me just show you the illustration of how it works on a completely general matrix. So in this is the usual graph representation of a sparse matrix. So every vertex represents 1 row and column. And if there's an edge from A to B, that means from I to J, that means A sub ij and A sub ji are non-zero. So suppose processor 1 has been assigned to compute AX, A squared X, and A cubed X for all these particular rows of the matrix. And here are all the other processors that have been assigned. So what does it need to do compute AX? I just follow the edges out 1, and that tells me all the data I need for my neighbors. I follow the edges out 1 more, so I'm just doing breadth first search, 1 step, 2 steps of breadth first search. I get all the green ones, those need to be communicated. And if I want to do 3 steps, I go out 1 more edge to the blue steps. So the simple partitioning that I did for the tridiagonal case turns into a graph partitioning problem because I want to minimize the number of edge crossings, and that's a classical high-performance computing problem, lots of software there. And then I need to decide what order do I execute all of these blocks in, and I'm not going to go from top to bottom as I did in the tridiagonal case. It turns into a very small traveling salesman problem, and that optimizes the order. And the same idea works for general sparse matrices. So that was GMRES and what we needed to do for GMRES. The mathematics gets a little more complicated, but we can do pretty much every Krylov subspace method. So here is the classical algorithm for BiCG stab. And the question is, how do we make it communication avoiding? Here's what the algorithm is. I'm not expecting you to read it, but let me just tell you it works. But I just want to illustrate that these 2 matrix multiplies in the classical algorithm turn into 3 calls to that matrix powers kernel that I just told you about. I need to compute 3 bases, and then it all works. And all of these dot products turn into 1 matrix multiply of a short fat matrix times a tall skinny matrix. And that's easy to parallelize too. And we got, as I said, 4x speedups by doing this. Okay, I'm doing okay on time. So now I'm going to stop doing linear algebra briefly and move on to machine learning. But are there any questions about linear algebra? Yes?
So what if like the k gets relatively large in GMRES?
So k is a tuning parameter, and depending on your problem, you may discover, all the examples we've ever done, k has been pretty small, order 5-ish. There was one example where it got up to 15, but it's a tuning parameter because you're doing some extra work. There is redundant work as you increase k, and so when that starts to get too much, that it doesn't pay off anymore, then you stop. Okay, so let's talk about the algorithm that most directly derives from what I just showed you. What I'm going to do is take that idea of unrolling the iterations from a Krylov subspace method. We can apply that to coordinate descent, which is one of the most popular algorithms in machine learning. And so just let me illustrate this with lasso. So lasso means I want to minimize not just the 2 norm of ax minus b, the residual, but I'm going to normalize it by adding in a multiple of the 1 norm, the sum of the absolute values of the entries. And this is a very popular algorithm. But the idea applies to ridge regression, proximal least squares, support vector machines, all sorts of different examples here. And this works as long as this is nonlinear because I have absolute values and stuff, so I can't do all the tricks that I did before. But you can still make some progress as long as the nonlinear part is just inside the innermost loop. So here is classical coordinate descent. I'm going to repeat a whole bunch of times. I'm going to randomly select a data point, a column of my vector A. I'll solve a minimization problem, which will have an absolute value in it or something, and I'll update a solution vector. And if I count, and these are all vector operations, so if I count how much stuff I have to move, the flops is the number of steps times the length of a vector divided by the number of processors. I take h steps. Each one involves a reduction, so h log p messages, and I'm sending order h words. So the communication avoiding one is simply going to not just optimize one point at a time, it's going to optimize s points at a time. So s was, well, we called it k before. So now s is the amount I do the unrolling. So instead of, so I'm going to take s columns of my matrix. I'm going to compute the gram matrix, so the dot products of all the rows of that submatrix with itself. I'll still solve the minimization problem for all the data points in there, and I'll update the solution vector. So now I have a little matrix multiply and a bunch of vector operations. And so do I get any benefit from doing this? And the answer is yes and no. Red means no, green means yes. So I'm actually increasing the amount of flops by doing this, and I'm increasing the number of words, but I'm decreasing the number of messages that I send because I only have to do a reduction every s steps. And so this is not as beneficial as for linear algebra, but we still can get like 5x speedups, especially if you're running in an environment like Spark or MapReduce or whatever, because their communication is really expensive to do these reductions. So it's worth doing some extra flops and sending extra large messages in order to reduce the number of messages proportionally. Okay. So let me move on to neural nets and image net training. And so what I would like to do is take the ideas I've already talked about and apply them to all the big matrix operations inside training a neural net. And so let me just remind you at a high level of what these algorithms do. I want to minimize a loss function, and so I'm just going to compute the gradient of the loss function, which is a function of a whole bunch of weights inside my neural net, and go downhill. Right? This is a classical thing. And there's something called the learning rate. How far do I follow the gradient down at every step? And there's the gradient. So this, and I'm going to do this by picking what's called a mini batch of B data points. I can't afford to do it on all my data, so I just pick a subset of the data, compute the gradient, and go downhill in that direction. So this describes a lot of algorithms. So what's the data parallel version of this? The data is too big to fit in one processor. I'm going to partition it. So every processor is going to get the batch size divided by p points. They're p processors. Everybody's going to have a copy of all the weights. And then each processor is going to compute its contribution to the gradient just by computing the gradient with respect to the data that it owns. And then everybody, to get the full gradient, I have to sum it up. And so there's a sum over all the processors. Then we can take a step in each direction. And there's a p in the denominator because I'm actually averaging all of these components. Okay, So there's the formula that I need to make run as fast as possible, and I want to increase p, right? I want to use parallelism. So what are the bottlenecks if I try to do that? Well, if I keep b, the batch size, fixed, then I'm going to have less work per processor, so I'm going to have smaller matrix operations, and so I'm going to get locally communication bound. But also, of course, the cost of each reduction is going to grow because if I increase p, the size of the reduction is going to be log p. So what do people try to do in practice? They increase the batch size along with the number of processors. So if you keep b over p constant, then you'll maintain the processor efficiency. Everybody's going to, the local matrix multiplies will always be of the same size. And if you're lucky enough to converge in the same number of passes over the data, an epoch is a pass over the data, then you'll be doing it with fewer reductions. You'll be doing the same work with fewer reductions, and you'll get the benefit of that too. So what goes wrong when people just try this straightforwardly? It's a different algorithm, and the convergence just is terrible, right? Because you're not computing the same gradients. You're taking different paths, and it just doesn't work as well. So people have been trying to work on this for a while. And so, for example, what Facebook did when they were trying to fix this, they adjusted the learning rate. So just backing up, the learning rate is how far I go in the direction of the gradient. And their idea was that if I increase the batch size by a factor of k, increase the learning rate by a factor of k. And they also had this, these are all very ad hoc things, a warm-up rule, which is you start with a slow learning rate, and then once you get closer to the end, you increase it. And that let them increase the batch size from about 256, which is their starting point, up to 1K for AlexNet, which is a well-known database of images. And they tried lots and lots of tuning, but they couldn't get past 1K. So the fix that, in this case, my student, Yang Yu, came up with was something called layer-wise adaptive rate scaling. So it turns out each layer of a neural net is basically doing a matrix multiply and then some nonlinear operation. And it turns out that at each layer, the relative change to the weights was very, very different by a factor of 233. In other words, if you'd used a constant learning rate, some layers would change a lot, some layers would change a little. And so they had to adjust the learning rate differently for each layer of the neural net. And then, so once they did all that, they got a factor of 135x speed up. So, and this is sort of now the state of the art. It's been adopted by a lot of places. So let me just look at ResNet, which is a particular neural net. And so they tried to scale up the batch size from an initial size of 32 up to 32K, all doing the same amount of floating points, so 90 passes over the data. They want to maintain the same accuracy, which they managed to do. And they do it on a variety of different platforms. This small one was a CPU and a GPU. But all these others are, let's just look at these three, which are all different numbers of nights landing. So it's the same processor, going from 16 to 512 to 2,000 nights landings. That is a factor of 128 times as many processors. This is strong scaling. And the time went down by a factor of 135, from 45 hours to 20 minutes. So it got superlinear speed up. And the reason is that the matrix multiplies in each processor got larger, and so they went faster, and that's why you got superlinear speed up. And so this is now the state of the art. It won a Best Paper Prize. It's been open sourced in a lot of different platforms so that people can use it. And a few weeks after my student hit the world record, Tencent in China adopted it, put it on their bigger machine, and got it down to 4 minutes from 11. So who knows what the world's record is now. OK. So now let me talk about going beyond all of these things to sort of arbitrary code. So let me summarize everything I've said so far, which is about optimal algorithms for things that smell like three-nested loops. So here's what I mean. Anything where I have three nested loops and I access three arrays inside where the subscripts are of the form ij, ik, and kj. Right? I could be doing many things there, but what we've proven is that the number of words moved between main memory and cache is the number of loop iterations, n cubed, divided by m to the 1/2. So here's how we generalize it. I can have as many loops as I want. So here I have k loops, for I1 equals something, for I2, for ... for ik. And I'm iterating over some subset of k tuples of integers. It doesn't have to be a cube. It can be some arbitrary, sparse subset. And I can have as many arrays as I like. A1, A2, A3, and they can have any subscripts. They can be simple things like I1. They can be I3 plus I4. They can have multiples in them. This is very, very general code. What I would like to do is generalize this theorem and the optimal algorithms we have for it to any code that looks like this. And here is the theorem, which we proved a few years ago, and it has just been accepted by a journal. It takes a long time in the math world. So it turns out that any code that looks like this, the number of words moved is lower bounded by however many loop iterations you are, which could be n cubed or it could be anything if you have a sparse thing, divided by the fast memory size to some magical exponent, which I'm calling E sub HBL. And HBL is an acronym from 3 famous mathematicians, so you can see this mathematics goes back to Holder, which is centuries ago. So people have been generalizing this. This is sort of a generalization of the Cauchy-Schwarz inequality to its ultimate form. And this uses recent results by folks like Terry Tao at UCLA, who's a very smart mathematician and was doing this for pure mathematics reasons, and my collaborator at Berkeley, Mike Christ. So what we can do is basically write down a linear program. I'll give you an example shortly. And the solution of the linear program is this magical exponent. I'll do it in a very simple case. So that's the lower bound. And what we recently proved is that it's always attainable. You can always find a tiling that attains this lower bound. And now there's an assumption here, which is that, that the size of the optimal tiling fits inside all your loop bounds. So just to give an example, for matrix multiply, what's the optimal tiling? It's a square root of m by square root of m submatrix. You do these little square matrix multiplies. But suppose I'm doing a matrix times a tall, skinny matrix multiply, a matrix times 2 vectors. Then I can't fit the tile inside 2 vectors, right? Because it would require square root of m columns. So it doesn't work. So this theorem here assumes that my loop bounds are all very large. But we've also been working on how do we do it in the case where the loop bounds are bounded. Can we generalize it? So let me now give you a very concrete example, again from machine learning, which is convolutional neural nets. So let me just draw a picture and explain what a convolutional neural net is, and then in terms of nested loops. So I have an image which with W by H, width and height, and it has a certain number of colors or channels in it. And what I want to do is filter it, run it through a filter. So I have a whole bunch of little filters of size R by S by C, and I have K of them. And what I want to do is take each one of these filters and move it across here and do a convolution. So I want to take this guy and do a convolution and get one number, and then keep moving it back and forth and sideways until I move it everywhere. And so the output is going to be, again, W by H roughly. I'll have K values, and that's going to be the output of my convolutional neural net. And of course, I don't have just one image, I have B copies, but they're all going to use the same filter. So how do I express this as a bunch of nested loops? I'm going to loop over all of the filters, then over all the height and the width of all the images, and then over the size R by S of all the filters, and then over all the channels, and then over all the images, and I compute this nested loop, where I have lots of subscripts, and most of them are nice and simple, but there are some of them that are added to one another. So I would like to find an optimal algorithm for that. In fact, the algorithm is a little more complicated. I just don't move this over by 1 at every step. I move it over by some shift, which are called sigma W and sigma H. So this is where all the time goes when people train their neural nets, running this particular algorithm. So what I'd like is a lower bound on communication for this and an optimal algorithm. So let me tell you what the lower bound is. So if I go back to here and say, what's the total number of iterations? It's going to be capital K times capital H times capital W, et cetera, et cetera. So let me call that capital N. That's the total number of loop iterations. M is the cache size. And it turns out that the lower bound on the number of words moved is the maximum of 5 different terms. And any one of them could be the largest. So the first 5 terms are kind of obvious. You have to write the output out once. You have to read the images in once. And you have to read the filters in once. So the size of the input and the output are kind of obvious. The next term in this max of 5 terms, it turns out it's the Nbody problem. If all the loop bounds are really, really big, this is really the equivalent to Nbody problem, which I'll say a little bit more about. But the point is, it's not m to the 1/2 anymore, it's m. So the denominator is much, much bigger, and I can go much, much faster. But that assumes that I can have very big loop bounds and very big tiles. So what if I have small filters, which is typically the case? then the math gets more complicated, but here's an explicit formula. It's m to the 1/2, which is the matrix multiply term, but it's even a little bit better depending on the size of the filter and divided by the size of the shifts. And so this is the lower bound, and any one of these may be the largest. And this is the one that is most interesting, that in the common case, the data doesn't fit in cache. One filter does, but you can't, you can't attain this particular lower bound. And you can imagine from this complexity that doing all of this proof by hand was not feasible. So my grad student Grace, wrote a Mathematica program that broke this down into 200 cases, and each one there's a proof and an optimal algorithm that's been generated. So we are still working on implementing this, but let me just show you some of the theory so far, which says that, and so this is on a variation of this called capsule nets, where the inner loop is actually, because these things keep getting more complicated, where this thing here is actually a 4x4 matrix multiply, because that's the latest variation on this. And in that case, we ran cache grind, which is a very detailed cache simulator to see how much traffic we could save. And the communication avoiding algorithm is in orange, and it's always the best compared to just the naive 8 nested loops. And that's much better than the matrix multiply algorithm that people use currently. Because the way people do this currently is that they take this thing and say, I'm doing a convolution, but if I just make lots and lots of extra copies of all the filters, I can turn it into a matrix multiply. And we all know there's an optimized matrix multiply somewhere to use. And that's what people do currently. So there's big speed ups potentially here as well. So partially inspired by last night's talk at dinner, I added one more example. You'll see why in a moment. So this is the simplest case of this theory, where I can actually write down all the theory, which is just 2 nested loops, to compute forces on pairs of particles, right? The Nbody code. So I have particles P1 through Pn, and I take all the pairs, I compute some function, and I update a force. And so what I want to do is find the optimal block size. So I'm going to block this loop. So instead of having just 2 loops, I'm going to have 4 loops. And the 2 innermost loops should hopefully just work on data sitting in cache. And so what I need to know is, what are the tile sizes for those 2 innermost loops? And it turns out I'm going to assume they're m to some exponent. So I'm going to have like m to the 1/2 or m cubed or something like that. I want to know what should my loop tile sizes be for the innermost loops. So here's the optimization problem. I want to maximize the amount of work I can do, assuming all the data fits in cache. All the data fits in cache means that the number of x entries has to be at most the cache size. The number of j entries has to be at most the cache size. How much work do I do? Since I'm taking all pairs, it's the number of pi's times the number of pj's. So what I want to do is maximize that exponent, subject to that exponent is less than 1, and that exponent is less than 1. That is a super simple linear program, and the answer is 1, 1. And so I'm just going to read in m entries of this, m entries of that, and take all possible pairs and do the updates. And that gets me down to a lower bound of n squared over m. And so it turns out that all those tricks that we use for matrix multiply, where I replicate the data, applies to the Nbody problem as well. So let me show you some more speed up numbers. So now I have 32,000 particles. I want to compute all pairwise interactions on 8,000 cores. So it's 4 particles per core, right? So you'd think this would be pretty communication bound. And what I'm doing is that same trick where I have not just 1 copy of the data, c equals 1, but 2 copies or 4 copies or 8 copies. And you can see the same trick works by just having 32 copies of the data, which means instead of 4 particles per core, 128 particles per core, so it's still very little memory. The communication cost, the green stuff, is completely gone. And I have perfect strong scaling for this problem. So, and it gets up to an 11.8x speed up. So where are there applications where people do direct Nbody calculations? Because you'd think, okay, most people are going to use fast multipole or something like that. Well, here's some examples. There's gravity and turbulence and molecular dynamics. In that case, it's 3-way interactions, because you take triples of particles and compute more complicated force functions. We got 42x speedups for that. Plasma simulation, electron beam lithography, but inspired by last night's talk, there's also hair. So one of the students from our group spent a summer at Disney working on their code to simulate Princess Merida's hair. She was in Brave and many other movies. And it turns out the way that they do the hair simulation, what they want to do is that when she, waves her head around and her hair bobs, it all looks realistic, right? Just as what you saw last night. So the physical simulation they do is that each hair is a long string of charged particles, all positively charged, so they all repel one another. And then when she moves around, there's some forces, other forces applied, and the repulsion makes the hair look realistic. And so this is now, his code is now used in that movie and all subsequent movies where they simulate hair. And so that's good. The one thing he learned that was a little humbling is if you only spend a summer internship 3 months at Disney, you don't get screen credits. But he still gets credit for doing the movies. Okay, so here's some other topics which I didn't have time to talk about. I talked about classical matrix multiply. You may all be wondering about Strawson, and there are lots of other things that are faster than n cubed. All the theory generalizes to that, and we have optimal algorithms and lower bounds. Somebody asked about network topologies. Yes, we can tell you exactly what your topology, assuming it's a 2D or a 3D or a 4D torus, how high does that dimension have to be to attain these lower bounds? That depends on the algorithm. For linear algebra, a 3D torus is enough. For a lot of new architectures have what's called persistent memory or non-volatile memory. And in that case, it's often that writes are more expensive than reads. And so the question is, can I change this theory to separately optimize the number of reads and the number of writes? And the answer is yes. And we call them write-avoiding algorithms. And so we have a separate lower bound for the writes than for the reads. And finally, this is a slightly different topic. The IEEE 754 Floating Point Committee, which I was a member of, just finished. And we just adopted a new instruction for floating point. And it makes floating point addition associative again. So if any of you are worried about running on multiple processors and getting the same answer every time you run it, even though your summations are being done in a different order, there's a new instruction for that. And we also can tell you how that affects all these communication avoiding algorithms. So needless to say, this is joint work with a large number of other people, some of whom I've given credit to. And so here's just a long list. I'd like to point out Kathy Yellick in particular, with whom I have collaborated very closely, not just on avoiding communication, but raising 2 children. But that sounds like a contradiction, but you just have to be careful about what kind of communication you avoid. So we wrote a 155-page survey article back in 2014 on the state of the art just for linear algebra. We're working on another book right now for SIAM on the whole field. And we're just starting, so that'll probably take another year or so. In the meantime, we teach a parallel computing course every spring, and at least one person, Chelsea, has already taken the course. You can ask her. And so it's offered every spring, and it's webcast. So we have students from about 20 other universities around the country who take it for credit. And they all get free supercomputer accounts from the NSF, and we've ported all the auto graders there. So to summarize, it's time to redesign all linear algebra, machine learning, Nbody algorithms and software, and eventually those compilers, so you don't have to know all this theory. And what it all has in common is don't communicate.
Thanks so much to Jim.
We have 20 seconds left.
We have time for a question or two while we're getting set up for the next talk.
Yes?
So one way of avoiding communications is to store multiple copies of the data.
If you have multiple processors, yes.
And so I was wondering how, for processors, for architectures like GPUs, which are memory bound.
So if you only have one memory hierarchy, vertical memory hierarchy, then multiple copies doesn't make sense. In the theory, you just have one copy of the data is the right thing. But if you have multiple processors with multiple GPUs, each one of which could have a extra copy of some of the data, then it would work. Yeah, so all of this sort of is recursive in the sense if you have a complicated architecture, you might have to apply the lower bound several times. Yes?
So for single node architecture, we have blocking and cache oblivious algorithms.
Yes.
Similarly, for a compute cluster, do we have communication oblivious algorithms?
So we have an algorithm called Karma. communication avoiding recursive matrix algorithm, and it does do that, yes. So yeah, if you look on our web page, there is an algorithm that does that.
So let's thank Jim again.